So welcome to lecture 42 of MCS 471 on an introduction to numerical analysis. So the topic of this lecture is to prepare for the final exam. So this is the second review for the final exam. It is review 4. So we had two earlier reviews for the two midterm exams. So the review of today focuses on the material between the two midterms. In particular, the review for the second midterm, the second review in this course, is also very much relevant. So in this review, there are 5 representative questions on topics that we considered. So they are representative, but they are not exclusive here. So that's in the second part. So in the second part of this lecture, I will go over the solutions to these 5 representative questions. In the first part of the review, I will repeat the essentials. So the most essential topic is the date of the final exam on Friday, 10 December, in the morning starting at 10:30. So the exam takes 2 hours. Here are the most important parts of the exam. So first of all, the exam is in this course online. So the course was ran this semester in a hybrid mode, which implied that everything could be online. But the hybrid also means that there was an in-class portion. So the in-class portion of the final exam is that you can go to the classroom to do the final exam there. So there is the on-campus version. If you have to be on campus that day, then going to the classroom at 10:30 and doing the exam there is the on-campus version. So the second most important part is that participation requires that you send an email. I will confirm that email in the evening of Thursday, 9 December. So if I do not receive that email, I will not email you the questions. I will, assuming then that you have given up on the course, which I hope is not the case. So these are the two important issues. The third important aspect about the exam is that all your solutions must be in a Jupyter notebook. And they must be uploaded to Gradescope. Also, they must be submitted before 12:30. So solutions that are outside the Jupyter notebook will not be considered. So the exam is online. So that's the part of the online aspect. We have been using Julia and the Jupyter notebook throughout the course. So the final exam measures also how proficient you are with Julia, with using Julia within the context of a Jupyter notebook. The other important thing here that I want to emphasize is that if you have a scheduling conflict, if you have an exam that conflicts with the scheduled exam of Friday, 10 December, then please let me know in advance. So in a way, I would prefer to know this before Thursday evening. So we can then schedule a makeup, most likely on Friday afternoon, also online and under the same conditions. So that's the other point that I did not mention on the slide here. Please check your calendars. Please check what other finals you have that week. If there is a final on that same time, there are rules which course has precedence over the other. There's also the rule that if you have 3 finals on that same day, so I mentioned the makeup on Friday afternoon. If you have 3 finals on the day, that might not be possible. So then we will find something else. Most likely then Monday morning would be then the day of the makeup. Okay, and I hope that everybody is still will still pass this course. So the default option that you will receive an F should not be taken. I hope that everybody will realize that, certainly also after seeing the review, that the problems that we have considered are quite understandable and quite doable. Okay, so for this review, we focus on the material after the first midterm and before the second midterm. One can focus the topics entirely on solving ordinary differential equations, for which we applied methods of differentiation and integration. And the ordinary differential equations were classified into initial value problems and to boundary value problems. So we will focus in this computational course on the concepts of numerical analysis. You should have some understanding on how Julia functions and Julia code works, but you will not be required to do any programming. This review is focused on 5 questions. I do not intend to overwhelm you. We have covered many topics, but if you want to focus, please make sure that you understand the 5 problems that are answered in this review. One way to prepare more actively for this exam while you're listening to this recording would be to make a Jupyter notebook with the answers of the questions. So if you have to answer a problem, sometimes you have to, you may have to run a Julia function. It's good for all the important problems that somewhere you have your Julia code ready. So we have covered many lectures. If during the exam is open book and open notes and open textbook, but if during the exam you will have to look for where to find something, you will run out of time. So another issue that I want to underline here, if you have more time, look into the homework problems. So many of the exam questions are coming from homework. Many homework problems are actually exam questions. So another good way to prepare, as I mentioned, was the second review, the review for the second midterm exam that contains more questions. And also all versions of the second midterm exam are important. So in particular, if you did not take the second midterm exam, then it would be good if you would practice one of those, pick one of the questions, and for 50 minutes, try to solve the problems without looking to the posted solutions. If you're really out of time, if you only have a couple of, if you don't have 50 minutes, then it might be good to simply compare the 3 versions for the second midterm exam and look for the problems that are common. There are many versions of the exams, but the most important problems are actually common. So that's the way the exams are structured. For the first midterm exam, we had problems that were common. Also on the second midterm exam, there are some problems that are appearing on all versions. So make sure that you can do those type of problems very well without looking at the course materials. Okay, so then we start on the second part of this review with the 5 representative problems. So the first problem is one of those questions that appeared on all 3 versions of the second midterm exam. So here it is phrased as review question. So framed into the context of solving an initial value problem, where we derive an explicit method using a method of numerical differentiation. A method of numerical integration. So how does the method of undetermined coefficients work? We want to determine weights. So in this context here, you have actually given the answer. So the weights are 5 over 12, minus 16 over 12, and 23 over 12. So what you need to find are the weights, and they are multiplied with h. So we have 5 times h over 12 as the first weight for the function evaluation that we will do 2 steps back. So we are at the current point, xn, fn, xn, yn, fn minus 1, yn minus 1, and fn minus 2 is the function evaluation at xn minus 2, yn minus 2. So we are at the current point, xn, yn, and we use the value, the function value at that point, and the 2 previous function evaluations. So we are going to derive a quadrature formula that uses 3 points. We already know the 3 points. We already know the 3 weights. So the purpose of this question here is to rederive, is to essentially your work, do the setup for the method of the undetermined coefficients. So why are the coefficients that way? That's essentially the question. Okay, so what is the setup here? We have 3 points. What are these points called? Well, xn, yn, xn minus 1, yn minus 1, and xn minus 2, yn minus 2. It's important to realize that the function that we are considering is in 2 variables, although the second variable, the y, depends on the x. So there's 1 independent variable. For this problem setting, it is important that we can relabel the points in terms of the step size. So h is the distance between the points, and we're going to use the integral between xn and xn plus 1, or with the relabeling of the points, the integral from 0 to h. So the method is based on the numerical integration, where we integrate, so we have a formula that we want to obtain. The left, so we have an equation, we start from a differential equation. So here is what we should see on this. Let me use another color. So we have this differential equation here, and we solve this by applying the integral operator. So the integral operator is applied to the left and to the right. We want to have an accuracy that is as high as possible. So let me now switch again to the red. So what we want to determine is this quadrature rule. So we want to determine the weights given the fixed points. So the points are already given. So the 3 points that we use are minus 2h for fn minus 2. For fn minus 1, we use minus h, and the current point where we are, we relabeled this. So the current point, we put this at 0. So the picture shows the relabeling. So in answering this question, this is more or less what you need to have in your head. So what you want to do is you want to translate, perhaps now again the blue color. So you want to go from the explicit formula to the construction of a quadrature rule. A quadrature rule with 3 points. And we want to determine the weights W0, W1, W2. We already know what they are. So W0 is 5 times h divided by 12. We want to determine those weights so that every quadratic function, so if the f would be a quadratic function, then this rule would be exact. That's the degree of precision. So we are now at the setting of the method of the undetermined coefficients. So the answer is in the 3 equations that are written here. So the 3 equations are expressing in the right-hand side that the 3 basis functions are integrated correctly over the interval 0h and with the points 0, minus h, minus 2h. So at the left side, you see the application of the quadrature rule with the 3 unknown weights. So we have 3 unknown weights. We have 3 equations. The equations are linear. So this is solving a linear system again. And as a result of that linear system, we will find the unknown coefficients. So we will find the values that were given. So the method of the undetermined coefficients is used to set up the system, the linear system in the unknown weights. Here is the solution. So this is extra. So if you are focused in an exam, then the answer in the previous slide is enough. Here is the check with SymPy. We set up the equations, and you see that SymPy will solve the symbolic linear system. So it's a linear system where the h is still a symbol. It will solve it symbolically. All right, so this is the first. So this was our first question solved. Let's move to the second question. So the second question is on extrapolation. So we've seen 2 ways of extrapolation to compute numerical derivatives, and we have seen the application of extrapolation to do integration, to speed up the composite trapezoidal rule. So it's important to know if your second question comes, what you have to apply. So typically you have to know if extrapolation is on a derivative, you will apply Richardson extrapolation. And also if you have an integral with the composite trapezoidal rule, that is slow, then you have to do Romberg integration. So here on this review, only Richardson extrapolation is used, but please review also the questions on Romberg integration. So typically, the problem will already have the answer in it. We know what is the derivative of the function f here. If you do not know it, apply SymPy. So knowing the exact answer will be very useful to know that your computations make sense. Also, it will be very useful to answer the question on the accuracy. So why do we apply extrapolation again? Well, we have the problem that the forward differences can actually only apply it with a very narrow range. So if we if you make h too small, then we suffer from round off. If we have h too large, then we are also too inaccurate. So there is kind of a critical range of h values, but we can greatly extend the range of the accuracy of our numerical differentiation by using extrapolation. So I'm spending some time on the question here. So it's important here, if you have this question, you don't see the title. So apply extrapolation. So this is the context of Richardson extrapolation, but the difficulty on the exam will be that second question will not have the header Richardson extrapolation. It will not have the header Romberg integration. So you have to know that extrapolation for differentiation means Richardson extrapolation. Also, what is important, and the data here is the range. So the function Richardson comes with some examples. So you have to adjust at least the function. So the function here is just like you would write it in Julia. Julia has very nice definitions of functions. We are at the point 0.5, and we start our forward differences at 1/16, and then we cut h in half in each step. So like we experienced in project 4, working with powers of 2 in the denominator of h is advantageous numerically. So the first step is computing those forward differences with the forward difference formula, and that will be the input to the Richardson extrapolation. So that's the main, so there are two computational steps that one has to do here. For the Romberg integration, you will apply the composite trapezoidal rule in step 1, and then do Romberg integration in step 2. And the last question is always the most important one: how many decimal places are now correct? So we will see how to answer that question in many ways. Here is the Richardson extrapolation. So Richardson extrapolation, it actually does already also the forward differences for you. So in a way, the first column will actually do the first step. What you need to apply so the tangent function can be immediately supplied in this problem. There is the point 0.5, and then there is the starting point, the 1/16. And we do our extrapolation steps. 1/16, 1/32, 1/64, 1/128. So the 4, you should be able to derive it from the sequence of steps that we take. The exact, if you still remember your calculus, then you can write down the exact value just like this, but SymPy is useful for this. The exact is useful if you want to solve the accuracy question one way. So you can also reason on the approximations on the columns. Here is the output. So the output gives a triangular table. The first column contains the forward differences. And we use the exact solution. So the code is not given here to compute a table with errors. It's a difference of two matrices. What is also important here is that when you print your numbers, always print them with sufficiently number of decimal places. So by default, you could do this with 16 decimal places. Here, the numbers were printed with 8 decimals after the dot, or with 9 decimal places in total. So that's important because we anticipate that we could have had 8 decimal places correct. So how could this happen? Well, look at the columns. So we have that the forward differences are expected to be correct of order h. So the last row was 1 over 128. So 1 over 100 in decimal notation is 10 to the power minus 2. So we look essentially at the last column. And each time we eliminate one order. So we go from 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 6, 10 to the power minus 8. So we could anticipate that we could have had 8 decimal places correct. So that's a good reasoning. If you reason, if you do not compute the table of errors, but you reason with the order of the forward differences, and with Richardson extrapolation, there is a Taylor series expansion in H. So each time we eliminate one order. But then there is also the shape of the function. So there is a constant that theoretically one does not know if one does not know the shape of the function. Here we see, so here is the other way how to see the accuracy. You compare the number of decimal places. So 6 is the answer if you use the exact answer. 8 would be the answer if you reason on the most optimistic way in which Richardson extrapolation is applied. If you do not compute the table of errors, you can also say, well, look, there are 5 decimal places that are corresponding in the 2 previous rows. So you could see Richardson extrapolation also as an iterative method. So 5 is also a good answer if you provide the good justification. So the justification is for these type of questions more important than the actual answer. All right, so we've done the first 2 questions. We are now to the middle of the review. Linear algebra is extremely important. So one could have said that this course was in the first half being more dominated towards linear algebra, and the second half was dominated by differential equations, while linear algebra is also important in the second part. So this is obvious when we look at differential equations with constant coefficients. So this is a linear system. It's a higher order equation. It's formulated in a quasi-numerical, quasi-abstract sense. So you are given the very specific constants that appear in the differential equations, but the initial conditions are left abstract. So this is a fourth order equation. We have four initial conditions. The question contains enough data that you can answer the most important question. As time goes on, what happens to the solution? And this is independent of which initial conditions that we pick. Is the solution expected to diverge, decay, and in both cases, is there an oscillation possible or not? You can, of course, gamble and say one thing. So you have three, or have mainly two choices, converging or diverging. But just writing that answer will not give you much credit. What is in this answer important is that you can reformulate this differential equation as a system of first order equations. So this is shown here in the context of a stability question. We have done this also when we did the boundary value problems, when we did the second order equation. So the fifth project to get started with this is essentially rewriting a higher order differential equation as a system of first order differential equations. So the question is not saying this. So even if you would have the title, well, if you have the title linear system, you can assume that something happens there. But on the final exam, again, you will have the question just as what is in black on the slide. You will not have the blue title. So there will be some computation here. So this is a review question. The review is more elaborate in the sense that you also have to solve for the roots of the characteristic equation. So how is the rephrasing done? So we have a fourth order equation in one variable y. We will have four equations in four variables, but all the equations will be first order. So the characteristic equation is obtained by replacing the derivative, so you could see it also like this. So here we have, by pure pattern matching, we have the 4 from the order of the derivative, and here we have the 4 that now drops to the index. And what is very important is the prime. So we still have a differential equation. So here the prime is a first order differential equation. So this is the characteristic equation. You can see what the dictionary is. So we have y3, and the derivative of y3 is y4. So this is why here we have the third order. This becomes y4. Then perhaps another color. Here we have the second derivative, and the second derivative here is y3. So that's why we can here replace y3. So we have the original equation that becomes an equation of first order, but has the 4 variables sitting in. So then we have the extra equations. So we have 3 extra equations that are also formulated here. So I'm having a lot of colors here. So these equation, yellow is probably not the right color. But here we have, if we read this now from right to left, we have our differential equations. So y prime 3 equals y4, y2 prime equals y3, y1 prime equals y2. So we have then 4 differential equations of first order. So if you have to solve this rather quickly, then the first four equations that are reformulated here are actually the solution. So it's kind of, if you would write this down on a sheet of paper, you would start at the fourth position first with the characteristic equation. So why is it a characteristic equation? Because linear systems are formulated in matrix format. That's what we did in the first part of the course. Now the matrix connects the original four variables with their derivatives. And the eigenvalues of this matrix are going to determine the long-term behavior. So this matrix is also called the companion matrix. They are the eigenvalues of this matrix are the roots of the characteristic equation. So here, because it's the review, it is expected that you can solve this. But it may very well be that, as I did on one of the versions on the midterm exam, you may have been given the roots, the eigenvalues, the roots of the characteristic equation. So once you have the roots, then we can answer the question. So here are the, so this is the output of the numerical root finder. So the first thing you look at is so the first important issue here are the real parts. They're all positive. And then we have the imaginary parts. So the imaginary parts will determine the oscillation. The real parts, whether positive or negative, positive real parts mean diverging, negative real parts means converging. So we justify this from the roots, but the reasoning is that the general solution is a linear combination of the exponentials. So the exponentials will be diverging if the real parts of the eigenvalues are given here again, all real parts are positive. That means that the exponential, as time goes on, the exponential diverges. We also have an oscillating behavior, but that's when it is diverging is actually less relevant here anymore. We go to infinity, but it will go up and down. And the oscillating behavior is apparent because of the non-negative imaginary parts. So the justification is that the roots of the characteristic equation are determining, so are actually the arguments of the exponentials. So the general form, so when it is a linear system, the general form is very clear. So this answers this question. All right, then linear problems are very important. And it is important to recognize when a problem is linear or not. So this is a second order differential equation formulated as a boundary value problem. And you should recognize that here we have the solution y, which appears non-linearly. So it can as a power, it can be like in the pendulum problem that you have the y as the argument of the sine function. So knowing whether a problem is linear or not determines whether your shooting method can stop after 2 tries. So here it's not the case. So this is a review question, and I take the opportunity to also explain quadratic extrapolation. So the interpolation was, so this is another use of extrapolation again, but it's actually also using Lagrange interpolation. From the first part of the course. So in this question, you are asked to compute the solution trajectories. It could very well be that you are given the outcome of the integrator, and then you will need to apply the extrapolation. Okay, so this is a bit redundant. So if we have already done the rewriting, so I will go faster here. But here you see that in this initial value problem and this boundary value problem, reducing it to an initial value problem is also requiring the rewriting. So rewriting higher order equations into first order equations is something that you will need to know. This is something that you may be familiar with already from the project 5, the way shooting is applied here. I will go a little bit faster over the code. What is important here is that we now have the input for an interpolation problem. So the input of the interpolation problem, let me make this clear. So the input is the point -1 with corresponding function value f1. And then the second point is the x1, which is 0, and then the corresponding function value is f1. So we are looking to represent the result of the shooting method as by means of a polynomial. And we are looking for where the polynomial takes the value at the end, takes the value 1/12. So here this problem is kind of nice because all the numbers are different. So we are working with the interval 1, 2. The exact thing that we want to know for the derivative would be the derivative at 1 at the start, and we want to compute the derivative so that we end at 1/12. So here we arrived once negative, so this is undershooting. And with the 7.2, this is also overshooting. So we undershot and we overshot with the shooting. So it's important that we are going to solve not for 0. We are, in some sense, we are looking for a root, but it's a root of the interpolating polynomial minus the target value. So the target value here that we want to obtain when we shoot is 1/12. And that answer to the solution here will actually give us the next value for the next guess. We can do this with Lagrange and with SymPy. And you see, we wanted to find the next guess. So this is a nonlinear problem. The question is often, is this a correct value or not? It will be correct if the problem was linear, if instead of the y square we had a y, or also we had an x. So be careful, an x square or an x to the power 3 is also linear. So that's often the confusion, or if time is happening, you may have a nonlinear function, but a function that is linear in y. So here, this is a nonlinear problem. So the first linear extrapolation will not suffice. And then we can apply Lagrange interpolation. with a quadratic interpolation. So here we are doing Muller's method from the first project, essentially. It's very regular and very much structured. With SymPy, we can solve a quadratic equation and obtain the closest guess to the next value. So here we solve this, so the details are kind of omitted, but you see that the next guess is already closer. So we have two values when we solve a quadratic equation here. So Q is a quadratic polynomial. Again, observe the structure. So we are not looking for roots. Well, it turns out to be a root problem, but it's not Q minus 0. So there's the 1/12, which is the end point in our given 2-point boundary value problem. All right, so I have 5 minutes left for the last question, which is also a 2-point boundary value problem, which now turns into a linear system where we apply the finite difference method. So there is a twist here. So it's a boundary value problem that is a Neumann problem. So we are given the derivatives. So it's very important to look at the primes. So the previous problem, the Dirichlet problem, where we were given the end positions at the end of the interval. Here we are given the beginning velocity and the end velocity. And we are having to try to also resolve for the initial positions. So in setting up the linear system, one has to determine first what are the unknowns. So it's very important that what you have in mind is the discretization. So you can draw that line in your answer, but it's important to get the dimensions straight. So we have the spacing between the points. So we have 5 intervals because we have the spacing 0.2. We have 4 interior points, but since this is a Neumann problem, we will also have the boundary value problems, which are the unknowns. So the dimension of this system is 6, not 4. So that's an important consequence of this being a Neumann problem and not a Dirichlet problem. How do we use then the boundary value conditions? We use the boundary value conditions by using central differences. It's important we have the x square as well. So from project 5, you will have experienced this. So the x in the right-hand side comes up again here in the discretization. So we have the spacings, so the x in the equation is replaced by the xi's, and the xi is I times h. So we have should actually point it out here, what is always common in the central difference formula is this. Then we have the y prime that is sitting in here. So the y prime, for that we use the central differences. And here again we have the xi, because the xi is coming from the x. So this essentially solves more than half of the question, setting up the general equation for this problem. This then turns into a system of linear equations where we use the boundary values to turn this into a completely determined system. So we have 6 unknowns, we will have 6 equations. So eliminating or using the derivatives, the given derivatives here. From the boundaries, we will have our 2's coming in. So we have the 2 times y5 that comes in here. Also, we have the 2 from the first equation. So this will be apparent in the structure. So I'm pointing here the 2 from the y1. So the 2 will also be apparent in the matrix. So the 2 will also appear with the y5, or we will have these conditions. So we always have a tridiagonal matrix. What is on the diagonal may sometimes change depending on where the y appears. Also here we do have the constants, so we have the multiples of h squared coming in. And this is because of the x that appeared in the differential equation. So with this tridiagonal structure, we can then solve it. So then this leads to a structured linear system. So here it is. What is important is that, so this will be the last part of the question, and actually the most important part. And this requires usually referring to the known errors with finite differences. We always use the same formulas, and we always have the h square. And this is where you use the spacing. So we have the 0.2. So the alternative question here would be, how accurate is it for 0.2? Well, we have 0.2 to the power of 2. We cannot hope more than 2 decimal places. What should the h be when we want 6 decimal places? Well, the h has to be 1 over 1000. So we need a system of dimension 1000. So that's another way to formulate the same question. All right, I ran over time. I hope that these 5 questions give you a good focus on the concepts that you will need to know for the second part on the final exam. So there is still one more review that will focus on the partial differential equations, essentially on the last question on the final exam.